All right, so we've got a puck with a mass of 80 grams is moving to the right at 1.5 meters per second. It makes a glancing collision with the second puck with a radius of 6 centimeters and a mass of 120 grams. The rims just touch in the collision and they stick together and spin after the collision. A, what is the center of mass of the system? And B, what is the angular speed of the system after the collision? So, a glancing collision is one that occurs where the objects do not hit with their center of mass in line. So the center of the line of the center of mass motion for this one is like this. And this is the center of mass for this one. Those two dotted dashy lines are not on top of each other. Because of that, it makes it a glancing collision. So head-on means that their center of masses are on the same line. Glancing, their center of mass is on different lines. So, it's going to make this glancing collision, and then they're going to stick together. And I drew the picture at the second half of the picture after it's already moved a little bit in the rotation. But right after the collision, or at the moment of the collision, you've got the little guy and the big guy, and I drew them so that the very bottom edge of the small disc is just tangent to the edge of the larger disc. So this one has a radius of 4 centimeters. The bottom one has a radius of 6 centimeters. And we want to first find the center of mass. So this one is, the center of mass of the big one is here, the center of mass of the little one is there. Where do you suppose the center of mass of this system is? Is it up here? Is it here? Is it here? Is it here? Probably somewhere right there. So we think the center of mass may be. Okay. Well, to find the x position of the center of mass, we add up m1x1 plus m2x2 plus m3x3, as many as we might have, over the sum of the masses. And the x1 and x2 are in reference to a place where you want x to be equal to 0. Where do you want to put your coordinate axis? So if you could put a coordinate axis anywhere you wanted to, where would you put that coordinate axis? I would put it at the center of the big one. Is that okay? I'll make it dotty. Dot, 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 dot. Okay. So then the x center of mass would be the mass of M1. Which one do you want to be M1? The little one or the big one? The little one. Okay. So this will be M1 and this one will be M2. So M1 is 80 grams. So is that 0.08 kilograms? And how far is its center of mass from the origin? (10 centimeters? Is that 0.1 meters? Plus the mass of object 2, which was 120 grams, so 0.120. And how far is its center of mass from the origin that you created? It's at it, so 0. And then divided by the total mass, which would be 200 grams. So 0.2 kilograms. So where's the center of mass? So that was 0.04 meters, which is 4 centimeters. So this little red X represents the center of mass. So now I've found the center of mass. Because these two disks will collide and there's no fixed pivot point, they're going to spin about the center of mass. That is where, if you were looking over top of it, that's the point that would not seem to be spinning. It would be moving to the right after the collision, but that would be the point that all of the disk pieces would seem to be rotating about, the center of mass. Okay? So, what is the angular speed of the system after the collision? Well, if angular momentum is conserved, the initial angular momentum is equal to the final angular momentum. And the initial angular momentum would be the momentum of the disk as it's moving in a straight line. The disk is not spinning to begin with. It's just moving to the right. How do we find the angular momentum of a particle that's moving? R perpendicular times V. So R perpendicular, though, is the distance. So remember, take your object, draw a little dotty dot 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 path to get right over the reference point. So this piece right here is R perpendicular. And it would be the distance from the center of mass to the line of motion. So what's that distance going to be? The radius plus 2 centimeters. So 6 centimeters away. So then our 0.08, 0.06, 6 centimeters away, times the velocity, 1.5. So this is M, R perpendicular, V. Now, after they collide, they're going to stick together and rotate. So then I need the moment of inertia of each disk about the new spinning point. So I'll need I for object 1 plus I for object 2. And that moment of inertia times omega must be equal to the initial angular momentum. Now this is where the I's get fun. So we said mass 1 was going to be the small disk. So after the collision, is the small disk revolving about its center of mass? No, it's revolving about the center of mass of the system. So what is the moment of inertia of a disk about its center of mass? 1/2 mr squared. But it's not revolving about that center of mass. So how do I find the moment of inertia of this disk about a parallel axis? Add d squared, where d is the distance from the center of mass to the new pivot point, to the new spinning point, to the new axle. I'm trying to come up with analogies and synonyms and things. Synonyms was a better word there. Okay, so then you'll have 1/2, 0.08 times its radius, which was 0.04. Remember, it was a 4 centimeter in diameter, squared, plus its mass, times the distance from the center to the new pivot point, which is 6 centimeters squared. So this is the moment of inertia of just the small disk while it is spinning about a new point. It's not its center of mass through its parallel axis. Then I need to find the moment of inertia of the big guy. So it's a disk, 1/2, 0.120, with a radius of 0.06 squared, plus, I'm going to go back up to the picture. So is it orbiting or spinning about its center of mass? Nope. It's spinning about a parallel axis. How far is that parallel axis from the actual center? 4 centimeters? All right. So then this will be the mass of the object times 4 centimeters squared. So ugly, but there is the moment of inertia of object 1. We're going to add to it the moment of inertia of object 2. And then we can multiply all this by omega. So to find the moment of inertia of this small disk, so the small disk is here. This is its center of mass, but it's going to be spinning about this point right here. So that's going to be the point that it spins about. Okay? So to find the moment of inertia, you need the moment of inertia through the central axis or the axis of symmetry, and then you need to add md squared. So for a disk, it's 1/2 mr squared, and then m times d squared. So for my little disk, it would be 0.08, the radius is 0.04, and then the mass is 0.08, and it's off center by 4 centimeters plus 2, because I've already found the center of mass, and it was at 4 centimeters from the center of the big guy, and they're 10 centimeters apart, right? So it makes it 6 centimeters from the small guy squared. So this is using the parallel axis. That's where this came from. The parallel axis theorem. So omega 9.47 radians per second. Woohoo! That's right. So we've got a wad of sticky clay with a mass of m and a velocity of v fired at a solid cylinder with a mass of capital M and a radius of capital R. The cylinder is initially at rest and is mounted on a fixed axis that runs through the center of the cylinder. The putty is moving towards the cylinder at a distance d above the center of the cylinder. What is the angular speed of the system after the collision, and is linear momentum conserved? So if angular momentum is conserved, because this is a frictionless axle right here, then your initial angular momentum is equal to your final angular momentum. Now initially, it's an mr perpendicular v. It's a point mass that is moving with respect to a pivot point that's defined. And then you're going to have the moment of inertia of the cylinder plus the moment of inertia of the putty, sticky clay. Cylinder and sticky and clay have the same, I'm going to call it sticky clay. There we go, times omega. And we want to find omega. And I feel like we've done this a million times, but little m is moving at a distance d that's perpendicular. Do you have any questions about where I got d as being the perpendicular distance? It's even drawn right here, the perpendicular distance. B. The moment of inertia of a cylinder is 1/2 capital M capital R squared. Now where is the putty going to stick? It's going to stick to the edge, and it's going to rotate on the edge. So what's the moment of inertia of the putty? Little m capital R squared times omega. Therefore, the angular speed of your system will be mdv divided by 1/2 capital M capital R squared plus little m times capital R squared. No calculator needed. That's why I love a letter question. Your momentum conserved in this collision. What do you think? Momentum is conserved when there are no external forces. The only force on the system is the collision force. What's in the center of the cylinder? Yes, and is it going to keep the objects from moving to the right afterwards? Yeah, so this axle applies a force, outside force, to the system that stops its forward progression. So if it were to hit and then slide to the right and rotate, then linear momentum would be conserved. But it can't. It's fixed. So actually the axle is going to absorb some of that momentum, so to speak, because it'll, shift, and there'll be what's going to happen to the clay? Did we watch it'll deform. That's right. We watched the video. Uh-huh. So, nope. P initial does not equal P final. Linear momentum is not conserved. All right, so now we have a projectile of mass m moves to the right with the speed v initial. The projectile strikes and sticks to the end of a stationary rod of mass m and length d that's pivoted about a frictional axis through its center. Find the angular speed of the system right after the collision. Determine the fraction of mechanical energy transferred during the collision. So let's do this. I did not make it very clear, which is one reason why I decided I wanted to do this one. But we're on a flat, we're looking down at this pivoting rod. Whenever I think of this, I think about the little spinners that are in board games. You know, the arrow, and you spin it, like you thump it, and isn't that thumping? Anyway, you thump it, and it goes, spins around and around, right? Okay, so anyway, so here's our rod, and it's on a frictionless surface. So we're on a surface or a table. We've got an overhead view of it, and we've got a projectile, so some sort of blob, and it moves and sticks to the end, so it's going to stick down here. So we've done the question where it was pivoting at the very end. We've done the question where it did have any pivot, but I thought maybe we should do this one. Find the angular speed of the system right after the collision. Well, again, if the initial angular momentum is equal to the final angular momentum, this is a length of d. This guy has a mass of capital M. This mass has a mass of little m, and this has a v initial. Then we need to m r perpendicular v for the particle. And then afterwards, we'll have I of the rod plus I of the projectile times omega. So little m, what is r perpendicular going to be? D over 2, perfect. V initial. It's little things like d over 2 that cause you lots of headaches when you're solving problems and wind up getting the wrong answers and stuff. So pay attention. And the rod about the center, 1/12 md squared plus, now what's the moment of inertia of the projectile after it sticks? You're going to treat it like a point mass? So m, what's r then? D over 2 all squared, and then times omega. Is that it? So m dv initial will equal 1/6 md squared plus little m d squared all times omega. Did I do that right? Multiply by 2. Oh, yes, because that was a squared. 2. I tried to be fancy. Just didn't work out so well for me. So then would you do what? 2? Right. Okay, can I do this then? Is that okay? Tell me if I did it wrong. But only if you're sure. Just kidding. Anyway, here's your initial, and then over 1/3 capital M D squared plus little m d squared. That's easy. God, I love a question that just has letters. We're done. Oh, I can cancel the d's if you want me to. I'll get out my big purple lightsaber. Meow, meow, meow. You don't have to simplify anything, actually. Nope. Actually, sort of leaving it as is a lot of times a lot easier for us to figure out what you substituted in. Yeah. It's fine. What's up? All right, next part. Determine the fraction of mechanical energy transferred during the collision. All right, so what kind of mechanical energy do we have to begin with? Is there gravitational potential energy? What's the system? Does it include the Earth? Well, what does it change height? So is the gravitational energy going to change? It's not. You can put the Earth in there if you want to, but your gravitational energy before and after is going to be the same because they didn't change. But we're going to have a kinetic energy, translational, initial. And then what kind of energy does the system have? The system of the rod and sticky projectile after the collision. Rotational. Very good. All right. So the fraction that is transferred. What is a fraction that is transferred? So is it the difference in what we had to begin with and what we have in the end divided by what we had to begin with? Part over whole. Does that sound familiar? A fraction? So that would be what? 1 minus EK rotational over EK translational initial. Rotational at the end, 1/2. The moment of inertia, this would be what? 1/12 capital M d squared plus little m d over 2 squared times the angular speed that we found squared. And we could come up here and use the ugly version of it, or we could use a slightly better version of it, but 2 mv initial over 1/3 capital M d plus little md. Divided by the initial translational kinetic energy. What's that? That's it. Oh, I forgot to square this guy. There we go. And this is your answer. The reader, me, can see that you did a moment of inertia times an angular velocity, angular speed squared, and I can see that you did a linear kinetic energy. And when you simplify it too much, it's sometimes harder to find, and if you make a mistake in the simplification, then it's even harder for us to figure out if you did the right substitution in the first place. Because on a question like this, your substitution, your method is going to be where you're earning your physics points. There are no points for algebra.